Okay, this is problem 729. I'll probably do this in 2 bits here. Basically, what it's asking you to do is to write a program that'll compute the maximum transverse shear. And what they want you to do is to have all these variables here be possible inputs to that program. And then it gives you some values, and it asks that you use those to check the program. So I'm going to split this kind of into 2 parts. The first part will derive the equations, and actually will I think we'll use the numbers that they give you and get one set of answers. And then in the second video, I'll develop a program using Mathematica, because it's relatively simple. But you can use MATLAB, or if you really want to program in C or C++ or Fortran, that's fine as well. But I think Mathematica is an acceptable programming language. Okay. So here's the problem here. All these variables, D1, D2, A, L, W, are all parameters that are input into the program. So we have to find the maximum shear stress in general. So it's a little tricky to get actually a, one equation that'll give us that. So, the program will have to follow the steps we do to solve by hand, as we would if we were by hand. So let's outline the steps we would do by hand and figure out how we would translate that into a program. So the first thing we need to do, right, is actually, we know to compute the transverse shear stress, we need to do VQ on IT. All right. We need to get the V. So we need to be able to compute the shear diagram, or the shear forces. So that would be sort of the step one. Actually, before we do that, we're going to need to also compute the reaction forces at A and B, because those aren't given, and I think that's really the only way to get it. You need at least one of them, really. Once you know the shear forces in the beam, you'll need to compute the geometric factors. There's 2 we'll have to do. We'll have to compute the I and the Q, and that's the Q for the max Q at the midplane, right? That's the Q of the upper half of the beam. And then once you do that, you can then compute the shear stress, which is going to be the maximum V times the Q over I times T. Right? So those are the steps. All right? I think maybe I'll do this in a couple of parts. Let's not put the numbers in yet. All right. So actually, since this is going to be a program, the nice thing about programs is you can sort of build complexity onto them as you go on. So actually, instead of hard coding the program just to deal with this exact loading situation, let's kind of generalize a little bit using superposition. The nice thing about this is really, once you kind of write this general program for a distributed load and for a point load, and maybe we could even do one later on for a linear distributed load, you can then just duplicate those parts of the code and do it for more complicated. Maybe there are multiple point loads, or a distributed load spans over the whole thing. All right? So I'm going to consider 2 cases, actually. The general distributed load case, right, where we just have the distributed load, and we'll add on to that the case with the general point load. And in both of these, the point load can occur anywhere, and with the distributed load, it can have any width, and it can occur anywhere on the beam. So in fact, it could be over the whole beam. Okay. So this is going to be W, and this is P. So then we're going to have the reaction at A, reaction at B, reaction at A, reaction at B. We'll call this case, we'll denote this stuff with a prime and this one with a double prime, because that's another case. Then out of this, we'll get the V from this case, and then the V max from this case, right? We'll have to, well, actually I should say this. We're going to add the two V's together, the V prime and the V double prime, and then we're going to find the max of V prime plus V double prime, right? And that's going to be the V we use. That's going to be the V max. That's the basic approach. All right? So we'll kind of break them up into two cases. And then if you wanted to add, like I said, other types of loads to the program, you can add that later on. And of course, you could take a similar approach to computing the bending stresses, right? We're going to do shear stresses, but you can also do the bending stresses. And if you want to do the bending stresses, a nice little trick, maybe I'll do, I don't know, probably not, but maybe I'll do a video as well, is actually you can then just integrate the shear moment diagram. Once you get that in a program, you can integrate that and get the bending moment diagram. Right? And figure out where the maximum location of the maximum bending moment is, and then compute the bending stresses off of that. All right, so that's kind of the notation we'll use, right? Okay. So let's look at the first case. Let's look at the distributed load case. Okay. We need to find the reaction forces. Well, actually, even before I do that, let's just talk about what this looks like. All right. So if you want to look at the shear diagram, this is the reaction at A prime, and here's the reaction at B prime. We can actually get a lot of information without even solving for those reaction forces. Although we could do that first, but let's just look at what we got here. These are all going to be positive. Well, actually, no. There'll be a sign change. Okay. There's got to be a sign change. So here's the x-axis. Here's going to be the shear force. All right. So we all should be experts at shear bending moment diagrams. So if you look at just this section when you start to go from A, just prior to where the point force is, right? That's the shear force acting downwards. So the shear force is going to be constant on that, and it's going to be equal to Ra prime. Okay? So now this value, this is going to be Ra prime. All right? Then once it hits, well, we can do the same diagram looking from the left side. And here the positive shear force would be up because it's a negative face. And here you can see that it would be constant, but it should have a constant value of minus Rb prime. It's negative minus Rb prime, right? And again, that goes just until the point where the distributed load happens. And then what happens to the distributed load? It starts to monotonically decrease. So you get this region that looks like this. Okay? So that is the shear bending that's the shear diagram for this beam. And you can actually see the maximum value is going to occur at one of the ends. It's either going to be Ra or minus Rb. Right? Just to draw, this is the, let's do something. I put the loads right on top. Here's the Ra load, and then at this point, is where we have the distributed load. And then here we have the RB. Okay? That's the shape of that diagram. All right, so let's find RA and RB in terms of the parameters W, D1, and this distance here, which is D2, right? Then obviously we also have L. This is L. Okay, so we know that, well, let's first do the moments and get one of these. Let's do sum of moments around A, or A. These are some of the Z moments around A. That equals 0. That would give me, okay, that negates out this one, so we get the RB directly. All right? This has an effective load going through here. Its value is going to be W times D2 minus D1. And the point which it goes through is going to be halfway between D1 and D2, right? So this is D1 plus D2 over 2, just the average, right? Okay. So then this is going to give me a negative moment minus W D2 minus D1 times its moment arm, which is D1 plus D2 over 2. Here actually you can see that the difference is 2 squares, A squared minus B squared plus A squared plus B squared. So that's actually D2 squared minus D1 squared. Makes it a little simpler. And then this one is going to give me a positive RB prime, and its moment arm is L, and that all has to equal 0. So that tells me that RB prime is equal to W on 2L D2 squared minus D1 squared. So let's save that. So that'll be like one of the first equations we'll use in our program. All right? So we can get this reaction force. So that'll peg that into the diagram. Now we know that the sum of forces in the y also is equal to 0. So that'll give me, obviously RA plus RB has to equal the total down load. So this tells me that RA prime is in fact equal to the total down force, which is W times D2 minus D1 minus RB prime. This is equation 2. We can leave it just like that because, in fact, we'll first compute RB prime and use that in here to compute RA prime. So those are kind of well-posed sequential problems. Now, knowing those two, I can draw this shear diagram, right? That's what it looks like. All right. Let's do the same thing for the double prime case, the point load case. Okay, so this is what you would have if you had a point load. All right. So if we have the point load case, this is sort of the double prime case, point load. So here's our beam. This one's actually even easier. Here we have RA double prime, RB double prime, and then we just have the point force P. This distance here is L, and this distance here is A, I believe, right? A. Yeah, A to the point force. Okay. So again, we can do sum of moments around point A, and that'll give me, this one actually is a negative moment, this one's a positive moment, so that tells me that RB double prime is equal to PLA, right? This one creates a moment, a negative moment, PA. This one creates a positive moment, RB L times L, divide by L, and there you go. So that's this one. So that's equation 3. Actually, if I were clever, I should call this 1A and 1B. We'll call this 2A. And now 2B is just going to be RA double prime is going to be P minus RB double prime. And again, this is logically well posed because, first we compute RB double prime and we can use that in here. Everything is known in this one. All right? Okay, what does this shear diagram look like? Well, this one's simple as well. This one's kind of obvious. Here's X. Here's V of X. All right? So if we look at the point up until, from A to P, right? The shear, positive shear is downward, and obviously that is just going to have to equal RA double prime. Right up to P. Well, I should do it up a little farther. Okay, and likewise, if we looked at on the right-hand side, right? Now positive V would be upwards. You can see actually V is equal to minus RB double prime. Right? Where this is minus RB double prime. This value here is RA double prime. And then right at the point P, right? The difference between those two is obviously this jump is P, right? So that's the shear diagram for the point load only. Again, the maximum values will be at the end. I don't know which one is maximal yet. It depends upon the parameters that get plugged into the program. All right? So, right, this is where the RA force is. Here's where P is located. And here's where RB goes up. Right? And now you have to imagine the superposition of those two shear diagrams. And that gives you the total shear. So I guess if I were to sketch that up, it would be something like this, right? Again, this kind of is going to depend upon case by case. Just do it once like this. We'll start up here at a value here. This is going to be RA prime plus RA double prime. They're both there. They will go at a constant value until we get to the point where the distributed load is. All right? And then that will drop linearly to the point where the distributed load stops. It'll still keep going on. And then we get to the point where P is applied, and that'll drop it down by P. So it'll be something kind of like this. Now, of course, this can change quite a bit depending upon, this program should work for cases where P might be inside the distributed load or to the other side. So this diagram actually is a little difficult to draw a priori, okay? Because it depends upon, here I've assumed that this is the region where the distributed load is and here's P. You could also have a case where the distributed load is over the whole thing. Or maybe P is at a point inside here, at which point this jump would actually occur right in here. Or possibly the P could be before the distributed load and then the jump will happen here. And then it would be, something like this. Drop down and then the linear slope right to there. Okay? So it depends. But these equations hold regardless of the fact. And no matter what's going to happen, you're always going to get a max shear at the end. In both cases, right? No matter where you put the distributed load, the max shear is going to be at one of the endpoints for both of these cases. So actually it's kind of an easy situation to deal with. We just have to look at the ends. Okay? We just need to consider the ends. There could be other other general loading conditions where you might not even be assured a priori whether, or I should say where, the maximum shear force will occur. But here you got an easier one. The authors took it easy on you. It's just going to be at the end. So we really only need so it's either going to be at A or B. So really, V at A is going to be the V at A from this case plus the V at A from the double prime case. And that's going to give me, by looking at these equations, this we get, whoops, we see that, right? This is A, this is the, we get this one from equation 1b, and we get this one from equation 2b. Okay? Likewise, I can get V at point B is VB prime plus VB double prime. So this one comes from equation 1a, and this one comes from equation 2a. Now the V max is going to be the maximum of those two, or I should say the max absolute value, right? And I should, yeah, that's fine. So these will have negatives on them, right? This is actually, RB, these are actually going to be negatives. Why are they negatives? Because the shear on the right-hand side is negative RB in both those cases, actually, right? Minus RB, minus RB. So these are minuses. And I should say max absolute value, right? It's the max of the absolute value. That gives me V max. This is what I'm going to use in the VQ on IT calculation, okay? So this, I don't know how to write this well, but let's call this 3A and 3B. That computes the total shear at A and B. And then let's call this equation 4. This is the one that computes the maximum V that I'm going to use in the shear formula, okay? Okay. All right, so where do we stand now? Well, now I've got this, the shear diagram, and I've got it in a form that I can program relatively easily. Now I need to figure out the equations to get I and Q. I guess I should mention this, I do, my research area is doing computational work, so I'm kind of used to this stuff, but I'm also always interested in how to teach people to start to do more computational type of problems. And I think this approach actually, especially when you get started, is a good way to do it. Write out all the equations you need first, before you even start to go program, okay? And then we'll talk about the programming steps. We kind of go step by step and build it up. We don't just start from line 1 and go all the way through, but this is sort of building process. Okay, so let's get the geometric factors. This is pretty easy. Let's get, we want to calculate I, all right? So this beam is symmetric. All right, so I don't really need to explicitly find the neutral axis. I know the neutral axis is going to go right through the middle, okay? Because it is symmetric. All right, the flanges are all the same. Yeah, it's all the same geometry. Here it is, right? So the flanges have to be the same side. I mean, the flanges are the same. Okay. So we'll break this up into 3 sections. Section 1. Section 2, and Section 3, which is really the same as Section 2. I need to write a little bigger, I guess. That's getting a little tough to see. Okay, so the I for Section 1 is just going to be 1/12 base times height. The base is T2. The height is going to be the total height minus 2 times T1. That's the flange height. Cubed. I should probably keep this picture down here, right? Maybe I could do this. Let's put that down in the corner. We'll do it this way. I think that works. Is everything on the page? Yeah, it's close. If I work that way, it's a little better. All right. The I of section 2 is going to be the I of itself around its centroid. Then we'll have to use parallel axis to shift it, right? So it's going to be, oops, I forgot the 12 on here. I'm sorry. So its I is going to be 1/12 base. The base is B for the flange. And then the height is T1 cubed. All right. Now we have to shift that by parallel axis. The area is going to be B times T1. That's the area. And now the distance from the neutral axis to the centroid is going to be the height divided by 2. That's the distance from here to here. And then subtract half the flange thickness. Okay? That's the distance to the centroid, and then we square that because it's parallel axis, right? So actually I can write this as take the 2 out of here, that's a 4. So we get B T1 on 4 H minus T1 squared. So we'll use this equation and we'll reuse this equation. We'll call this 5A and 5B. So we use this to compute the 2 i's, and then we can use equation 5C, which will give me the total I, which is the I from 5A plus 2 times this I, because there's 2 flanges. All right. Now that computes for me the total I for the shape. Now we need to compute Q, right? So now we need to compute Q. And this is going to be the Q just of the top half, because the problem wants you to find the maximum shear, transverse shear, which is always going to occur at the midplane here. So it's the Q of this composite section, okay? So Q is Q of the 2 shapes. Well, I can probably write this in one equation, I guess. No, let's keep it in 2, I guess. Yeah, we'll call this shape 1 and this shape 2. So Q for shape 1 is going to be the area, which is T2, that's 2, times H on 2, that's the area, and it's not H on 2, excuse me. It's going to be T2 times this is going to be not H on 2, but this is H minus 2T1 over 2, right? This distance here is H minus 2T1. We divide that by 2. And now the distance from the neutral axis to the centroid is going to be that same distance divided by 2. So it's this distance divided by 2. So that would put 4, that puts it 8 down here, right? Because that 2 came from this total distance, so I square that. So that's the Q for shape 1. Now we do the Q for shape 2, and its area is base times T1, and the distance is going to be H minus T1 on 2. This is H on 2, right? So that's that distance, okay? So this would be, we'll call it 6A, 6b, and then 6c. Q is going to be Q1 plus Q2. Not 2 times it, because there's only one of those. So those are the equations we're going to use to compute Q. All right. So where do we stand? Are we done? Well, I think we are, basically. We have everything to do the program. All right? I have... Well, do I need an equation? What is my equation? Do I have an equation? Here's an equation. Okay. So first, we're going to compute the reaction forces for the point load and the distributed load. Knowing those, we can get the shear diagrams for both of those. Okay. We figure out the maximum shear. It's going to be at one of the ends. Then, once we know that, compute the geometric things we need. And then, finally, I guess at 7, we get the max transverse shear. It's the V max, it's the Q, it's on I, and this is on T. So V max, that's the one we got from equation, where is it? I forget where it is. Equation 4. I got this from equation 4. Q I'm going to get from equation 6c. I I'm going to get from equation 5c. Well, T, you know, T is just going to be, I guess I could write it as an equation, but T is just going to be T1 or 2. I think it's T2. Web thickness. Right, T2. Thickness of the web. Okay. All right, why don't we pause there? It's a good, actually stop the video here. And I'm not sure what I'll do next. Maybe I'll write the program and then, no, I'll solve the problem and then write the program. And it really doesn't matter which order you look at it. You can do either one, but that's probably what I'll do. Okay?